This is instruction for Brian Bondwell. Bond energies have been measured by chemists for many years, and they're very important to understanding why reactions occur. So each type of bond, like this H bonded to H covalently, has a bond energy. I'm going to show you what that means here in a diagram. So question 1, consider two oxygen atoms that can double bond to create an O2 molecule. Relevant bond is right here. O double bond O, 500 kilojoules per mole. This graph, it's a funny kind of graph, it's a very important graph in chemistry, is a potential energy graph. The oxygen atoms that are unbonded will be high in potential energy. So here I'm drawing two oxygen atoms, each one with 6 valence electrons, 6 dots, unbonded. High potential energy. They will naturally bond to form molecules. So there's a molecule, and it's at the bottom of this graph, meaning bonded state is low potential energy. So this is called an energy well. A bonding well. That's why it's Brian Bondwell. That's the fundamental concept of every bond. It forms a well, a potential energy well. Atoms will fall into the well naturally. Question B says, well, what does that mean in terms of real life? Why are there very few unbound oxygen atoms in our atmosphere? Why aren't there these O single atoms? A good answer is to say, once bonded, once they're in the well, it requires a large amount of energy to separate. 500 kilojoules per mole is a lot of energy. And that's what's needed to separate the oxygen atoms. It's like a cost. I'll write that here, cost. Most atoms are not that rich in energy. So you can imagine that if it costs 500 kilojoules to split up, and the average molecule is only 50 kilojoules, they won't be splitting up. They'll have to stay together till they get enough kilojoules. If you were trapped at the bottom of the well, it would be very hard for you to escape. You'd need some help. Here's question number 2 of Brian Bondwell. First question says, next to each bond, show the strength of the bond. Strength of the bond using energy values. So here we have CH bonds, which according to the table are 410 kilojoules per mole for each bond, not for each atom. So maybe I'll point specifically. There, we're talking about the bond. The bond has an energy value, but it's not a positive energy. It's a well. It's a negative energy value. So it may be valuable to you to think of these as negative numbers. But the graph is the best way to show what we mean. So here's a funny looking graph. It's a potential energy graph. It's a well, but it has stair steps in it. So let's imagine since there are 4 bonds, we can think of it as 4 steps or 4 stages. At the top, we could have a carbon with its 4 valence electrons and 4 separate hydrogen atoms. Nothing's bonded. It's very high in potential energy. So this is the highest potential energy state you can have, where nothing's bonded. The next stage we could have would be we've made a bond, and we still have 3 hydrogen atoms that are unbonded, but we're getting lower in potential energy. Then we could have carbon with 2 bonds and 2 hydrogen atoms. And finally carbon, well, not finally, but next to last, carbon with 3 bonds. It would still have 1 leftover dot, and there'd be a hydrogen unbonded. And finally at the bottom we have CH4. This is the lowest potential energy state. In chemistry, low potential energy, the word that describes that is stable. So with these atoms, the most stable state is the CH4 molecule, and that is therefore the state in which you would expect to find these atoms, not as separated high potential energy entities, but as the low potential energy stable molecule known as CH4. So that's what's essentially said here in B. This structure that has 1 leftover bonding spot right on the top, you can see it. There it is. This is relatively higher. Well, it's higher in potential energy, and that in chemistry means unstable. If you think about it, the molecule in its very deep well will have a hard time escaping. In order for this CH4 molecule to escape the well, to break its bonds, it's going to have to climb all these stairs. 1, 2, climbing the stairs, and that's not easy. Climbing stairs is hard, just like for humans climbing stairs it takes work, whereas falling down the stairs is easy. You just let gravity do its thing. Here you let potential energy do its thing. So whereas CH4 with all the bonding sites filled is low potential energy. That's stable. That's the natural state. Things that are stable appear in nature. Things that are unstable don't appear in nature.